it's 11 o'clock and we have about an hour to continue the very interesting discussion that we had this morning. And before I introduce you to the people here, let me just make one single remark. I'm a terrestrial scientist, and I've been involved very much in climate research, in atmospheric chemistry. And you know what I feel in your discussion this morning, perhaps a bit contrary to what I'm accustomed in when we look or fine-tune our knowledge on the Earth itself, is that what you're talking about is really frontier. It's really inspiring. It's new. It's getting into the unknown, like you don't hear very much anymore when we deal with the planet Earth. So it is inspiring. It is really fascinating. And I'm really happy to lead, to moderate this discussion. So you see the name here. Maybe I will ask everybody to make a very, very short introduction. But before that, I think Mike would like to say a few words. So we're going to give him priority.
Thank you, Guy. When the organization expressed its relief that I'm retiring and said that for compensation they would finance a workshop of my desire, I decided to bring these disciplines that have been presented here together. I had great help in doing so with the scientific organizing committee with Matthias and Tim and Guy and Valentin, who unfortunately, because of aura commitments, couldn't be here. I think we picked great speakers. I learned a lot, and it's an inspiration to follow all these fields. To me, that I have a background in stellar evolution theory, what is appearing with the research on extrasolar planets is promising that to bring up the following analogy. 100 years ago or so, the Hertzsprung-Russell diagram, by looking at the spectral type of stars and their luminosities, their surface temperatures appeared, and there was just sort of this crazy distribution of stars of all kinds of ages and makeup, and stellar evolution theory, and then with the help of evolution simulations, if you want, made perfect sense to 99% of the stars that we have observed. Right now, the few planets that have been found, 4,200 or so, of course, look confusing. They have already told us how about planets that we didn't expect exist, quite a few of them. I'm kind of envisioning a science where we will have sort of a Hertzsprung-Russell diagram of planets, only that it will be multidimensional. You can't do it in a plane. But at some point, it will make a lot of sense, and it will teach us, give us more certainty or uncertainty about the stability of our planet. Thank you.
Okay, thank you, Michael, and we wish you all the best. And we hope really that this workshop, which was there to celebrate you, has really reached its goal, and that we know all the important role that you've been playing at NCAR over the years, and first scientifically, but also as director of HAO. And so I think we need to thank you very much for all your dedication and engagement for NCAR and for your field, for your discipline. So let us maybe introduce yourself by just saying your name, your institution. Of course, Eric, we just heard you, so it's just a repeat. But
me, Eric Wolf, I just spoke. I'm at CU Boulder down the street in LASP.
Svetlana Berdugina, Leibniz Institute for Solar Physics, Freiburg, Germany.
Jean-François Lamarck, Climate and Global Dynamics here at NCAR.
Natalie Battaglia from UC Santa Cruz, formerly of NASA Ames Research Center, just moved to Santa Cruz recently.
Jim Casting at Penn State, and I'm not in astronomy, I'm in geosciences and in meteorology and atmospheric sciences.
Can I have the projection, which are a few slides, just to introduce our subject today, and just to remind you what the question is, and the question is, how could the broader atmosphere or atmospheric chemistry community contribute to the study of extrasolar planets and habitability? And in order to start the discussion, I just put 3 or 4 slides together. Nothing really new. In fact, I just wanted to show the paper that I looked at a few years ago, inspired me very much. This is in the 90s when Jim played a real important role leading the field into those questions. And since then, of course, models have been developing, are more complex. A number of people have been trying to move from reality to models, using, of course, observation to help them, but trying really to use universal equation to simulate essentially a number of bodies that are in the universe. And of course, planetary modeling has been very much on the agenda. A large number of groups have been looking at different planetary atmosphere. And I took here from François Forget, who was cited several times. By the way, we had invited him to come, but he's in the Antarctic at the moment, and so he couldn't come. But he took a few lessons from basically modeling the solar system. By noting, number one, that general circulation model work, a few equations, simulate the planet with a realistic complex behavior and produce strong prediction capabilities. He also mentioned that GCM components are valid on various planets without major changes, which is kind of encouraging so that we can use these tools. It's going to be done in a minute. And then we have, of course, sometimes the GCM fail, and that's when, of course, things become interesting, and he listed here a number of reasons for that. I'm not going to get into the details. So are we ready now to move from the planet to the or extrasolar planets? And he believes that, yes, generic climate models can be developed. We heard also example this morning. Eric gave an example with the NCAR model. And so, yes, towards a universal climate model, is that something doable? Maybe that's one of the questions we're going to address today. And so what I'm going to ask is to have the different members of the panel here, maybe to start with a statement about how they see the problem involving, how they see this connection between planetary scientists and Earth scientists, climate modelers, atmospheric chemistry, dynamicists, meteorologists, whoever are involved on Earth and would perhaps be able to use their techniques, their approaches, their methodologies to address interesting frontier problem, exciting problem, I must say, on other bodies of the universe. So, Eric, maybe you start.
Okay. Well, thank you again for having me here. And First, I want to say that Francois Forget and his group at LMD are perhaps unarguably the leaders in 3D climate modeling of planets and extrasolar planets. Their group has been doing it for 20 plus years, perhaps even longer than that. And I would say that the strength, in my humble opinion, the strength of their team is that they've had a collective effort, not just for the generic model, which is separate from their Mars model. They've done Saturn, they've done Pluto, they've done mini Neptunes. I know that there's a paper on Archive recently where they have adapted their model for Saturn with a very high resolution and a cube sphere grid. And their strength has been in their togetherness and their unification of their efforts, where many of the other modeling teams in the papers I was showing, with the NCAR model, for instance, we're loosely collaborated doing somewhat of our own thing. And it's hard to, in the quest to have a universal model, which I think is definitely doable, and I think Francois's group is paving the way there. We really need to coordinate our efforts together. But it's a rare thing, because I had a huge list of models of teams doing 3D modeling of planets and extrasolar planets, and you have Francois's group, and then the NASA Model E team. Only in the last few years have started to put some effort into supporting that model. But all the other teams we're kind of separate, doing our own thing. So I think it's definitely a reasonable goal to work towards a universal model. You can look at the NCAR model where you have water as a advected condensable species. Well, it wouldn't take that much work in order to start generalizing things, where you can have a generalized advected condensable species. And perhaps the biggest technical hurdle, probably the first and biggest technical hurdle, is having a radiative transfer scheme put in the model that is flexible for the user to come in and start choosing their atmospheric composition. So as far as the 3D models, I think that's it's definitely doable. It just will take a coordinated effort to do it with different models and with CESM. And then for their application in the near term towards exoplanets, so last fall there was a meeting at Goddard titled Rocky Planets in the Era of JWST. And while there have been many of us, including myself, who have indulged in habitable zone planet modeling for years, and there's lots of interesting and cool theory and models that we can run, but for JWST, if we're thinking rocky planets, we're going to be seeing more stuff like, imagine a Mercury-like planet around an M dwarf star. Hot planets interior to the M zone, the habitable zone, is something we may do. Those, along with hot super Earths, bigger planets, mini Neptunes, and hot Jupiters. So if we want to meet the JWST data, we have to even further evolve our 3D models to being generic enough to handle these really weird planets and weird climate states. So that's in the near term. In the longer term, hopefully JWST will deploy its folded segmented mirror, because LUVOIR is based on the same design. So, yeah.
Excellent. Yes, please don't forget the sun to all this. Sun is important for all the planetary physics, and I would like to compliment this conference and Michael for this idea, which I already told him in person, that this combination is unique on this conference. You put together here solar, stellar, and planetary science and exoplanetary science together. This didn't happen yet. I haven't seen it. If you think about these four topics, and there was going on already for the last 2 decades, lots of solar-stellar connections, discussions, and lots of geophysics, exoplanetary discussions. Yeah, and I've been more on solar-stellar side, and I can say that yes, it is difficult to communicate, because these are different languages, different cultures, and different type of data that we have in solar-stellar. And experience is such that you have a huge conference like Cool Stars and you have a solar session, it's only solar people there. And if a stellar session, and it's only stellar people there. And there are very few who goes in between. And it's something like this, like you mentioned, yes, it's hard to see how in practice this collaboration happens between geoscience and exoplanetary science, because everybody busy with their own problems. On the other hand, my personal experience is that we do solve the same problems. We solve the same equations. We use different math approaches, which is nice to learn from each other, but we solve the same equations, radiative transfer, global circulation. We do it for the sun, we do it for the stars, we do it for the Earth and for exoplanets. It's all the same physics. And that's something we have to start with, like maybe listen to each other, learn to understand each other's language. For instance, I was talking to some microbiologists, and they were complaining that it's hard to talk to astronomers and to do astrobiology together. Very few astronomers are capable of understanding biology's language. So it's probably this kind of intercultural and interspecies communication, I would say. I mean, this is a very good analogy. You meet alien. First, you have to meet alien, yeah? Second, you have to learn the language of the alien and then understand intentions and maybe work together. So first things, it's good to meet and then good to speak the same language. So that's what my kind of piece of.
Yes, I could riff on that forever. But I think there are two main points I'd like to communicate. One is that we can't understand the planet unless we understand the host star. This is as true today as it was 25 years ago when we discovered the very first exoplanets. And those people that discovered the first exoplanets were stellar astrophysicists, myself included. And there are many ways that this idea manifests itself. Of course, you're familiar with how planets have had their demise by being shown that their signals were due to stellar activity, right? And today, astronomers are trying to build better instruments to get down to the centimeter per second instrument noise level so that we can detect Earth analogs through the Doppler method. But the stickler is stellar activity. There's a graduate student at Santa Cruz and many others who are trying to use innovative statistical techniques to model stellar activity from calcium H&K and concurrent photometry to back out or decorrelate those noise sources, and it doesn't always work. It works for some stars, but not for others. And we don't know if that's a sampling issue or if it's an issue of intrinsic stellar physics. But it's a problem, and that needs attention. And keep in mind that for every planet that was shown to be a false positive due to stellar activity, there were at least 10 others that were thrown away from the observing queues because they were deemed too active. And we're throwing away really great objects with known planetary systems from transits. And that's lamentable. And so that's one thing. In fact, all these K dwarfs, for example, that we love, they're a sweet spot, right? M dwarfs are great, but they have deep convective zones, and there also just aren't that many of them that are bright enough. GJ1214, famous exoplanet orbiting GJ1214, that star has a V magnitude of like 15. TRAPPIST-1 has a V magnitude of 18. So, you know, the M dwarfs are great, but they have these problems. The K dwarfs are really interesting, but they also tend to be more active than the G dwarfs, and we tend to throw them away more frequently. But activity manifests itself in other ways. When we do photometry and we're working down at the part per million level, and then we do it as a function of wavelength, all kinds of systematic errors come into play, including stellar activity. So we've only begun to see how stellar activity rears its head when we're doing spectroscopy. And that's going to become a big problem in the future. So those kinds of studies are very interesting. Now, it's been said that Webb is not a life finder. It's not even tailored to do atmospheres of Earth analogs. It will not do that. But I want to emphasize that in order to understand what life is, we must understand what life is not. And formulating the null hypothesis is just as important. I think that the detection of life is going to be based on a statistical study of the atmospheres of large numbers of terrestrial temperate terrestrial planets. So formulating that null hypothesis is very important. Understanding a broad range of exoplanets and the physical processes that lead to the features we observe is going to be our hard work of the next 2 decades. And that work is interdisciplinary. I can't emphasize that enough. I can give examples. For example, at Caltech, there's a team inspired in part by the study of hazes in Earth's atmosphere, have identified various instabilities related to how dust flows through gas. And that looks like it's going to solve a very interesting problem with how planetesimals assemble in disks. Who would have thought that something operating in the Earth atmosphere is also operating in protoplanetary disks, forming planets? We're doing these studies. All of this work is being done, but we don't make these connections until we talk to each other. And that's really important. That's just one example. I could come up with many others. I don't know where the decadal is going to take us. I think it's going to be very difficult for the decadal survey to recommend, I'm going to say 16-meter class telescope in space like LUVOIR. I think LUVOIR is necessary. I'm not so interested in HABEX. I'll state that right up front because, again, I think that the search for life is going to demand a statistical sample. The 16-ish meter telescope is about the largest thing that we can fit into a current rocket fairing. And given the issues with Webb, I think it's going to be hard for the decadal survey to recommend something like that for the next decade. But however it goes, it doesn't really matter. Maybe we'll end up with a far IR telescope that does transits, transit spectroscopy. Regardless, it's all about exoplanet atmospheres going forward. So I think those are my primary messages.
Okay, well, I already had my say on habitable zones. Let me just mention one other problem of interest to exoplanets that hasn't been talked about, but that NCAR might have expertise on, and that is atmospheric escape. I mean, it's sort of come up tangentially, but in the early Earth and on many hot Jupiters, hydrogen escapes hydrodynamically, and that problem is understudied. There's a lot of expertise on upper atmospheres. I worked with Ray Roble here, who's one of the experts on upper atmospheres. I had a postdoc, Feng Chen, who worked on escape for a while, and he spent 2 years here at NCAR picking up physics from the upper atmosphere, the thermospheric GCM that Ray and his colleagues do. And so I think actually, and this field is understudied, and NCAR could play a role in that as well.
First of all, no, I'm okay. I'm just gonna just 4 out of 5. Well, that's fine. No, I can just speak about them. And so, just a little word on my background. I've done a lot of global chemistry climate modeling for the Earth, nothing for other planet. But so my expertise is really more on the connection between atmospheric chemistry, mostly gas phase, and the Earth's climate. But over time, I've done a fair amount, well, at least some paleoclimate simulations. And so, I was reading some material, and I'm really sorry, first of all, that I could not participate in the workshop, which sounds like it was super interesting because of my life as a lab director, which, as Michael knows, can be fairly overpowering. But I was doing some reading, some of Eric's paper, or some people working with Eric, where it was mentioned the DMS flux, and I was like, oh, well, that's exactly what we do here for the study of our planet. Things like DMS and biogenic fluxes, whether they come from methane, and others, is exactly what we do for a living. And so this seemed to me like, you mentioned CESM. I was the CESM chief scientist for about 4 years, so I know this model very at all levels. And I think this is one of those areas where we haven't really tapped into the connection that can be done with the physics, the chemistry, that is of relevance to the Earth, but can already be applied. And so the connection between the two communities is actually really significant. Echoing Jim's point, and I don't know if Dan is still on the line, so I'm working with Dan Marsh, who is also in Leeds, and we've been starting to look at using our flagship whole atmosphere model, WACM, which most of you probably, well, maybe some of you do know, where it's a full dynamics and chemistry from the ground to 150 kilometers. I mean, also now with levels above up to 500 kilometers with ionosphere. But our interest has been in the early Earth, trying to look at what is the structure of the atmosphere under, say, before the Great Oxidation event, and you're at 1% or 10%. What are the transitions that the atmosphere goes through? And if you look at it with a model that's been vetted and hugely used for the current atmosphere, then you at least you have a sense that some of the basics, physics and chemistry is probably well represented. So you hope that will still apply 2 billion years ago. But so one of the aspects that we're looking at right now, and I'm not supposed to say anything, so I won't, about hydrogen escape. There is some really fundamental questions that you can use even in a model that's extremely expensive to run. It's extremely complicated, and you can only maybe run it for like the equivalent of 50 years. But there's still some very fundamental questions that you can pose. I like the null hypothesis is really good. So that's one thing that we're really targeting. And there is actually, I don't know, you may not know yet, but Dan is actually organizing an exoplanet, what we call cross-working group, here at our CESM workshop in June. For that very reason, let's start the discussion on what is needed, new radiative transfer scheme, new physics, and some other characteristics that we could change. And then the other way is also what can we use with the, say, a present day or a pre-industrial or an early Earth, and try to put the equivalent of an observation, a satellite looking at the Earth, what it would look like, such that we know this was favorable for living conditions. This was not what it would look like from the outside. So that's all I have.
Okay, thank you, Jean-François. Let me make a comment in terms of engagement of the community towards these common problem between geophysicists or geoscientists and planetary scientists. As you know, I have a foot in Europe very often, and I see in Europe a number of climate research labs that are not particularly devoted to planets, to become really engaged into issue very similar to one we have discussed in this workshop. I mentioned François Forget, CNRS. It is a laboratory of dynamic meteorology. It's not a laboratory of planetary science. These are meteorologists, climate people, who just say, well, we need to move in the direction of, for example, planetary atmosphere, because we will learn quite a bit, and they can do good achievement. My own institution in Germany, the Max Planck Institute, has been using the HAO model to look, for example, how and when the Earth would get out of the habitability zone if, following the brightness of the sun in the future. So it'll take a few million years, but these models, for example, provide very different models than what you have been doing. And so there are scientific issues there. So I see, in other words, the climate community that traditionally works on the Earth climate becoming really interested in this. I don't see it so much at NCAR, for example, up to now. And I think I was going to ask you a bit about the reason for that. It seems to me that, for example, an institution like NSF, which is supporting NCAR and a lot of the research, is still very much divided into different sections that do not necessarily have this holistic approach. I mean, even in the Earth's atmosphere, you have the dynamicists, you have the chemists, you have the meteorologists, you have the climate people. It's very difficult to even get a global change view of how science should be conducted. And I say that for NSF, it might be true for other agencies. But certainly the connection between, let's say, atmospheric sciences or geosciences and other planets is not something that is easily done under the NSF constitution and organization. But you might have different views on that. So I'm trying to see, I mean, the science seems to call for these connections. And all of you have said that in the first round, but it seemed that there are barriers. So maybe we could talk a little bit about barriers and what should be done to change. You already mentioned one, which was the community needs to work better together. How do we do that? Jim?
Can I just comment on what you just said about NSF? Some of you may remember that NSF had a program called LEXEN, Life in Extreme Environments, which was interdisciplinary, like what you mentioned. The way that thing was funded was they stole a little money from a whole bunch of different NSF disciplines and put together LEXEN, and there was one person who advocated for it, and when that person left, everybody else wanted their money back, so it didn't last. So that's not a good way to do it.
I think Natalie can say more about it, but I was participating in several NASA workshops on exoplanets related science, and I can tell that they invite people from different divisions for those workshops, and you can really meet physicists from working on ionosphere, hardcore physicists working there, or you can meet meteorologists or like mathematicians, you know, really from different divisions, scientists. And that is always fruitful conversation, basically. And people identify the problems and look for solutions from different directions. And maybe that's the first step, to call for workshops from different divisions within NSF or within NASA, within NCAR, something like that.
Yeah, so where to begin? NASA astrobiology is changing. It's evolving right now. It was very much the NAI, the NASA Astrobiology Institute, which was an entity largely run out of NASA Ames. Multidisciplinary projects were funded. The people had talked to each other. The idea was to get interdisciplinary people to talk to each other. It underwent some criticism, maybe starting 10 years ago or so, that they weren't doing enough for exoplanets or the search for life on exoplanets, because that was emerging as a very promising pathway forward. And so Mary Wojtek at NASA headquarters tried to reimagine what astrobiology at NASA looked like. The interdisciplinary issue was a real challenge, because the reality is that there are organizational units everywhere, right, but at NASA headquarters as well, and money doesn't pass from one organizational unit to another. It can't cross borders. So the thinking ends up to be very stovepiped. And to deal with that, she put out a call for astrobiology proposals. They were reformulated. Now she's calling it ICAR, the Interdisciplinary Consortia for Astrobiology Research. And there are 5 different pillars. They range from prebiotic chemistry to exoplanet system science to early Earth, extremophiles and biosignatures, for example. And so they do have categories, but the idea is that people would propose and they would form teams that were intrinsically multidisciplinary. So she's encouraging that, and the idea is that those small number of teams, she can't fund very many, they're larger in scope, kind of akin to the NAI, but she was hoping that other entities, other program offices at NASA would then identify synergistic teams in their various disciplines that would join forces, and that these people would come together and talk to each other, and she would give some seed money to make that happen. And that's the pilot program for that was Nexus, the NASA's Nexus for Exoplanet System Science. It was started about 5 years ago, and we held various workshops on many different topics, biosignatures, the Habitable Worlds Conference that I think Svetlana is referring to, and we invited purposely interdisciplinary folks to come and talk to each other. So I don't know, I'm talking too much, but there are difficulties in making this happen, but I do see a lot of benefits. So I hope that it morphs into something very helpful in the future. For me, it has inspired me as I write my proposals to think about innovative ways of using the money, not just to do business as usual and fund our grad students and our postdocs, but to catalyze new collaborations, maybe by offering postdocs or grad students that are co-mentored by people in different institutes, or having innovative types of communication. But it's a challenge.
The barrier, the institutional barrier inside NASA or NSF or whoever. But let's ask us if there are other barriers and the first one is the scientists themselves, the scientific community itself. Are we sufficiently engaged, organized, dedicated to create this inter-geo-planet community that we would like to see? That's one point. The other barrier, perhaps, is that everywhere in the world, science become more and more strategic with final goals, as opposed to leaving to individual or group of scientists the freedom to really bring up new topics and to do things that might appear a bit crazy and that are not necessarily in the politically correct time. So do you see barriers also that maybe we should try to break as scientists?
Well, first I'd like to say that I think that amongst the younger scientists, there's a tremendous amount of enthusiasm for the multi-interdisciplinary approach. One may even argue the field is getting so crowded that as I said, we're starving for data. We need more data to feed all the young scientists like myself. So I don't think that's a problem. I think there's a lot of excitement for cross-disciplinary approaches with as was mentioned, the NASA Nexus program, the NASA Astrobiology conference. I know when I first went, maybe 10 years ago now, it's doubled in size in the number of attendees in that time period. And then, what was the second question you asked? I had something to say about that too.
So my question was, is there enough freedom for scientists to tackle problems that are not
yes and no. I would say that from my small perspective in proposal writing, that oftentimes some of these exoplanets, just thinking about what I do in climate modeling, you're writing your proposal plan for 3 or 5 years, and the reality is you're searching these unknown parameter spaces, and you're not quite sure what interesting things you're going to find, but the way the system works perhaps is you need to try to rigidly put that in an understandable box for the review panel when you're still trying to understand it yourself when you're putting it on the page. So I think that's a small barrier to try to overcome.
I think there's some really fundamental questions that you're asking there about how we fund our science. And proposal-driven science, that's what it's all about in the US, right? And more in Europe. It has its good points. It works very well, but it does tend to funnel you into areas that already have funding. And I was very blessed when I was a young scientist. After I was at NCAR, I was at NASA Ames for 7 years in the Planetary Science Division, and we had to write proposals, but not really. We were mostly, our salaries were funded. We were supported, and that's when I developed most of my climate models that I talked about in the habitable zones. Michael, I heard you talk about HAO and the fact that you supported solar physicists here to do work that was really fundamental research, and that maybe not a huge publication rate coming out of it, but things would not have been possible without institutional support. And so I think there's a room for, and Francois Forget's group in Paris is the same way. He's had 20 or 25 years of institutional support, and they're the leaders in the world.
So one point I'd like to make is that there might be the false sense that research is really isolated from the research that could be of relevance to climate change, or just Earth for present to future. And I do feel that to a large extent this type of research should be and probably will be more present, because it does push the models into slightly or largely different set of parameters, but it gives us insight to the inner workings of the system that we wouldn't look at otherwise. And for example, some of the work that has been done on the KT boundary was trying to look at what would we need to actually start looking at the aerosol layer after that. Well, they pushed a development of karma. There was that has become the reference for what we use for present-day climate research. And so I think it's really trying to also bring the elements that what we're doing for those extreme conditions also might have relevance for trying to do what we do for near-term future, trying to do it as best as we can by pushing the system into extreme. Oh, the Cretaceous tertiary boundary, sorry. The dinosaur extinction.
The dinosaur extinction. I wanted to add one more point. For astronomy, I think it's easier to get funding to do these kinds of innovative things because the search for life is so much on our minds and in the strategic thinking. What I'm hearing is it's more difficult for our colleagues in earth science and in the biological or life sciences. So I've been arguing, for example, trying to convince my dean and my campus administration to hire a biogeochemical modeler in the Earth and Planetary Sciences division. And, that requires taking these complex GCMs and basically dumbing them down in resolution and both temporal and spatial. So that's not really looked upon favorably by funding sources in earth sciences. So and I heard the same from Nick Hudd at Georgia Tech, who does origin of life studies, biochemistry, trying to create RNA-like structures spontaneously. And there too, for some reason, that's not looked upon very favorably by the funding agencies. But the good news is that I see a systemic change because the science that we're doing is so compelling, and the search for life and all of the exoplanets, for example, and even the solar system exploration has been so exciting that it is inspiring other agencies to pay attention. And I'm having some success at my university, for example, in doing these kinds of multidisciplinary hires. It's an easy case to make because it's just such exciting science.
Comments? Maybe we're going to ask the public, the participant, if you have any question or comments.
I have a question or comment. I think it's pretty important that there, at any institution, there be some sort of IRED funding, internal funding, that you can explore different things that may not necessarily be in somebody's strategic plan. As the director of an observatory, I have 7% director's discretionary time. I can do projects that people hadn't thought of. Betelgeuse became dimmer in December, and so we have a program of looking at Betelgeuse in the far infrared and to do this. This was not organized funding. At JPL, when I was manager of the science division, we had obviously a wide range of scientists, the people working on the HAES and Titan, as well as our atmospheric physicist and a geophysicist and astrophysicist. We were able to fund a number of projects, interdisciplinary projects through this. I don't know how other institutions do this, but at least I've been fortunate to have some freedom and additional funding that is not directly from NASA or from NSF to have this flexibility. Apparently, Michael, you have too, so I know at least 3 examples.
Yeah, I agree with essentially everything that the panel has said, but I think one ought to look into reality. And I'll throw out another idea. For example, the stovepiping that the NSF and NASA have done in the past. I had a really interesting solicitation from NASA, namely write a short note of what interdisciplinary science ought to be done by NASA. They're actually asking for how to do interdisciplinary things that were how to get out of stovepiping. I found that really interesting, okay? They actually asked for information on how to do it. Okay, what I want to mention is that it's very important to do interdisciplinary science because that's where the major discoveries have been and will be made. We all realize that. We all want to do it. But let's just for a moment think of the complications. It's really, if you stay in a very narrow topic, you have a chance of keeping up with the literature, going to the meetings and writing papers in less than 80 hours a week. If you really want to do interdisciplinary science, you have to now follow several people, several fields, each of which have their own literature, each of which have their own scientific meetings, and now you're talking about a huge amount of time, and you have to learn different languages and different people and so on. So it's going uphill in terms of one's personal time. But so I'm just trying to make the point that yes, indeed, we should do it because that's where the discoveries are, but there are complications. Personal complications.
Can I just quickly respond to that? That presupposes that we're doing science in a vacuum alone. My experience is that we don't, publications, in fact, projects that we're doing today are growing in scope. They require so many facets of expertise to make them work. I don't think that we have to know everything. I think we just have to talk to each other. So an example, I was talking about how dust behaves in a gas and how it influences a circumstellar disk. So there was a project that was led by Ruth Marie Clay, a theoretician of planet formation, talking to Ji Zhang, who's in the Earth and Planetary Science, who does cloud microphysics. And from that collaboration, Ruth didn't have to understand the cloud microphysics, or her grad student, but it led to a very interesting result about how we measure the carbon to oxygen ratio in the disks. So just by collaborating, you don't have to know everything. You just have to talk to each other.
Yeah, Jeff's introduction of reality it's always kind of depressing. But I want to do more of the same, and maybe even worse. And so, it's my observation that science tends to move in fits and starts, and when it takes off is when somebody finds a way to get a lot more scientific progress out of their own effort and the available technology and resources than had been noticed before. And that leads to a great burst of activity in some field, which goes on for a while and then kind of dries up. All of the low-hanging fruit has been picked, and it gets harder and harder, but there are more and more people in the field, and eventually it loses relevance because somebody else somewhere else has found another new soft spot where they can jump in and make a lot of progress. A reasonable example of this in solar physics, I think, is helioseismology, where if you look at the amount of progress that was made in the first 10, 15 years after Deubner and company figured out that, golly, the P modes were really acoustic waves in the sun. What do we do about that? And then, indeed, the capabilities to learn more about the sun that way got exploited and taken to the ultimate conclusion that solar noise sources will allow in a fairly short period of time. And now people do it, but it's no longer the hot thing in solar physics, and it probably won't be ever again. So what if we're in the same boat in exoplanets, and the soft spot that we found to probe that has given us more for our money, more for our effort than we could have ever reasonably expected is that there are transiting planets out there, and that gives you all sorts of opportunities to learn things. And so now there's a huge culture building up around that. I don't know what the right response to, suppose that's a correct diagnosis, then what do we do about it? What should our individual actions be? What should our community actions be? And, do we just carry on and try to push the limits of techniques we know to their ultimate end at no matter what expense, or do we find some other angle into the problem of understanding what other planets look like that is more promising? So, anybody care to expound on that depressing scenario?
Well, I agree that transiting planets are the thing of interest right now, and I think that will maximize our knowledge about transiting planet atmospheres, hopefully with JWST. But there's an obvious step to go beyond that. When you go to direct imaging, you see so much more. You see the planetary systems around all the nearby stars. You don't just see particular planets, you see all of them at once. And so there is an obvious path forward, but we have to, I'm just hoping the astronomical community makes the decision to take that leap, because I think that's what we really need.
I'll make a completely unrelated comment, but, and it's related to the fact that I'm clearly not a native. I had to learn the language, which took a long time. But my children are bilingual, and it didn't take them any effort. And I think this is where education and bringing students right from the start into a multidisciplinary angle, you actually learn the language. The young people, the older people, me included, have a harder time learning a different language. They don't. And so I think, to me, that's where the optimistic view is that we actually know how to make people who will be able to learn different languages and speak the different languages.
Okay, I want to say a keyword which I have not heard very often today and in the previous days is biosignatures. So I wonder, and anybody who would like to respond, how to make progress regarding detection, determination, exploitation of biosignatures in the future, and what we could learn about it.
Anybody wants to answer that? Jim?
Oh, there are those of us who have thought a lot about biosignatures. In fact, there's a literature going back to the early 1960s on it, and some of the ideas haven't really changed. Most of us think that if you had the simultaneous detection of oxygen and methane in a planet's atmosphere at appreciable concentrations, that's a pretty good biosignature. And there are other biosignatures. Oxygen by itself is a more controversial one, but in many cases that would probably be a biosignature. So we haven't talked about it at this conference, but believe me, there are a lot of people thinking about that.
Other question in the back.
Following up on what Jean-Francois was saying, that it helps when you're trying to sort of solidify multidisciplinary science to get a terminology straight. And first of all, I'd like to thank Michael for bringing this symposium together. It's been really fascinating to see all these areas coming together like this. And in thinking about it, I've been thinking about this for a while now, it seems like what we're discussing can be summarized as a terminology of stellar planetary system science. That's what we're all studying, whether we're studying the sun, whether we're studying the space weather, as we call it, the interaction of the sun with the Earth in particular, or whether we're studying other stars and other planets. It's all one sort of science that we're aiming towards here. So if we start to say to people that we study stellar planetary system science rather than we're studying heliophysics or we're studying exoplanets and things, maybe this will help get that unified language that the young people can then learn upon going. It will also help, I think, break down the silos that we see in NASA and NSF. For instance, once you've been in this field for a while, you begin to think, why are the planetary and heliophysics divisions separate at NASA, for instance? There's all these historical reasons, of course. Well, the planetary people study the planets and they like rocks and things like that, and we study the stars and heliophysics. But really, when you get down to it, we're studying the same thing again, the interaction of a star with its planets. And it doesn't make a lot of sense in some ways to have those be completely separate divisions within NASA. that are trying to address a lot of the same problems, but yet have completely different divisions and languages and funding streams and silos. Same thing in NSF. When you look at the solar physics at NSF, most of it is done in the astronomy program under MPS, whereas most of the stellar planetary system science, as I would call it, or space weather, is done under geosciences and the AGS division, or the AGS program. Again, a very artificial silo, which is, I think, unhelpful in thinking about this. But if we begin to think about these commonalities in terminology, I think we can make some progress, perhaps, at least with the young people.
So we're getting close to noon. Is there any last comment? Otherwise, let me just conclude here by putting maybe a bit light my views on in a very general way. We are scientists, and as scientists, we have a responsibility, which is to make knowledge progressing. Of course, society is supporting us, and so we have a role to play to respond to the societal demands. But society expects us also to move their curiosity to fascinating times, in fascinating aspects. I might have been too much in the Max Planck system, where basically science should be basically planned, or the research should be planned, decided by the scientists themselves. And I think that today we see a lot of constraints that are coming from society, from governments, from administrative desire of controlling essentially the way we're doing science. But I believe that we have to stand against that a bit and just make sure that, you know, our role of making knowledge progressing, being curious to attack other issues, bringing disciplines together, as it was said. I mean, we should just remember that, you know, 200 years ago, 300 years ago, scientists were at the same time philosophers, physicists, chemists, medical doctors, and this specialization has come really with the Industrial Revolution. But now we're going to a new revolution, which is going beyond the economic revolution into more like a cultural and knowledge revolution. And so I think as the world evolved, the place of the science and the scientist needs to be maintained, reinforced. And so we have to probably organize ourselves much better to attack new problems like the one we are discussing here, being more interdisciplinary and more curious for topics that are not necessarily the one that are fashionable in the funding agencies. But we have to tell the funding agencies that we think that the interesting problems are sometimes somewhere else. So I think that concludes perhaps the panel. I think that now Matthias, we have a conclusion by Phil, if he's ready.
I wonder if I could show just a few slides. I don't have. Sure. So would you like?
Are you doing that? If I could have.
You are.
I wanted to add this one other thought, and that is, if you look at, and that is an interesting document to read, the document that led to the foundation of the National Science Foundation, and the absolute emphasis that this foundation was to ensure fundamental research. And if you look at the language that NSF leadership has led NSF to evolve to now, then the emphasis of the short-term goal of directed research has been gotten stronger and stronger, thereby giving up on this original idea and becoming much more a mission-oriented agencies like it is the obligation of the scientists to broadly advocate to restore the original idea. I believe that is essential in order to get out of this micromanaging of science in terms of plans that are called strategic, but they're only tactical if you look at them. Yeah, that's what I wanted to say. Bill is still.